Good morning from Zurich. My name is Gregor Dumpert and this is my virtual IEEE ICC 2021 presentation. The main area of interest of this presentation is magnetic induction with its modern uses not only in RFID and NFC, but also wireless power transfer, wireless sensor network communication and localization, especially in challenging media like tissue for biomedical applications, embodied networks, medical microrobots, underwater sensor networks, underground sensor networks. Main motivation to look at magnetic induction are resonant multi-turn coil designs, which allow for strong near-field links, for example, for efficient power transfer. And also the magnetic field has good material penetration properties at low frequencies. And for this work, it's important to note that this means a free space model is often an adequate representation of the link. One problem that magnetic induction suffers is misalignment loss from suboptimal coil orientations. So when they are anything other than coaxial with their axis orientations. And for reasons of mobility or application-specific reasons, the orientations can be random even. And that means we get random misalignment losses and a random and unreliable link. And to the best of our knowledge, this is not well understood yet, especially not in terms of statistics and outage behavior. And to study that, which is the topic of this talk, we can draw inspiration from certain analogues in well-known and old radio topics, where it is well known that bad antenna orientations can cause a link to fade to zero, so you get an outage. This can happen even in free space when you have just a line of sight path. But when you hit the zero of an antenna pattern, or when the receiver orientation is orthogonal to the direction of the impinging field, and random antenna orientations cause a random fading channel. There are various radio papers on that, and the fading channel statistics they determine the outage behavior. So if, for example, the outage probability, diversity exponent, outage capacity, the typical things that are studied in a master course in wireless communications for relay fading and for rise fading. But here we talk about a different fading channel, and we follow the same storyline for magnetic induction with random coil orientations. We present the first communication theoretic study on the subject, and we describe the channel statistics and outage behavior in closed form for the near field region and also for the near far field transition. And we show that this is a particularly drastic fading channel. It's much worse than radio fading even. Some related work would be here, a rather classic paper on coil misalignment, no random modeling with a focus on accurate description of the channel coefficient and power transfer efficiency between two coils. We used random modeling in our paper here, and random modeling was also used in this paper with the focus on connectivity of magnetic induction-based ad hoc networks with random positions, random orientations. Now let's cut to the chase. We will first discuss the dipole model that we use in this work. Why a dipole model? Because it is an accurate description of a magneto-inductive link if the coils are appreciably smaller than the link distance, here the link distance here. We have a transmit dipole, which represents the transmit coil. So the orientation here is the coil axis orientation, also here coil axis orientation on the receive side. Unit vectors OT, OR, and we have a transmitter to receiver direction vector. The quantities that describe this link are the complex valued channel coefficient, the amplitude gain, and the power gain from transmitter to receiver is the squared absolute value. The channel coefficient is described by this formula here. For the case of weakly coupled dipoles, it has here this factor alpha with some technical parameters, cubic term, square term, and the reciprocal term. K times R is the wave number times the link distance. So when this is much smaller than 1, then we are in the near field region. When it's much larger than 1, then we are in the far field region. Here we have JNF. This is the near field alignment factor between -1 and +1, and also the far field alignment factor with the same value range. We note that when we are in the near field region, then the channel coefficient is directly proportional to JNF approximately, and to JFF in the far field region, which will be important later on. A little detail on the alignment factors, just to give you an impression what these are. These are inner products of the receiver orientation and some field vector. And for the near field case, the field vector is the typical near field shape that everybody has seen in school. And for the far field, it's this radiated far field pattern. All right, now the assumptions that we use in this work in terms of random coil orientations are, we assume that the transmitter orientation and the receiver orientation both have uniform distribution on the 3D unit sphere and with statistical independence. So this is the ultimate in random coil orientation that you could think about. And we are interested in the distribution of the now random channel coefficient H, so that we get from this formula as a result of uniformly distributed OT and OR. And we note that in the near field region, the distribution of J and F will determine the distribution of H, same in the far field, or likewise. And things are more complicated in the transition region where the joint statistics are important. All right, let's have a look at the near field region with some far field flavor in here. Let's first look at the PDF, so the marginal PDF of the alignment factor here for the near field and also for the far field for comparison. We already discussed the value range between -1 and +1. We see this interesting PDF shape here, which is derived in the paper. And we see, actually it's constant here for a certain interval. And we note that it has a finite value at 0, which will be important. All right, now let's look at the outage implications. In the near field region here, the power gain will be proportional to JNF squared with some prefactor here. And let's look at the PDF of J and F again, as discussed. It has a finite probability density around 0. And what does that mean? That means J and F squared will be close to 0 quite often. And this can be seen in terms of the CDF scaling. So the CDF of the power gain has a square root dependence for small arguments. And that unfortunately means that a fading event where the power gain is close to 0 is quite likely to occur. And the mathematical detail on this can be seen here. If you are interested, you can reproduce the scaling behavior in a few steps here. But we move on to the technical performance implications of this result. And we find that when we look at the outage capacity, which is the information rate over an AWGN channel that is guaranteed with a certain probability epsilon, we find that for small epsilon or small SNR, that the outage capacity is proportional to epsilon squared. Now, this is disastrous scaling. That means if we require any kind of reliability in terms of a small epsilon, then the information rate will be tiny. If we want to divide our epsilon by a factor of 10, we have to reduce our information rate by a factor of 100. Likewise, if we look at the bit error rate scaling for a BPSK modulation, we get the asymptotic behavior that of SNR to the power of -1/2. That means the diversity exponent is 1/2. And that means reliable communication is contradicting random coil orientations. Now, these results, they concern a link with an active transmitter, actually. And when we have a passive transmitter, like in RFID with load modulation, things are even way worse. Then we get the 4th power here, and we get a diversity exponent of 1/4, which is a disastrous fading behavior. Now, that was the near field region. Now let's discuss the far field, the near far field transition region for a moment. To understand the near far field transition region, it's best to rewrite the dipole model that we use in a slightly different shape. We can write the channel coefficient as an inner product of the receiver orientation and the complex valued field vector, three-dimensional, given by this expression here. And in the near far-field transition, now this field vector will have linearly independent real and imaginary parts. And this is the key effect here of why the transition region has better outage behavior. We get polarization diversity, and which is a well-known concept from radio, but it's at the bottom of the phenomenon here. And to study now the statistics of H in a preliminary step, we assume that the receiver orientation is random, but the transmitter orientation is not. That means these are non-random, and the vector V is non-random as well. And then in this case, we can nicely study the statistics of H in terms of the joint statistics of its real part and imaginary part. And we obtain a PDF result now, joint statistics of real part and imaginary part. The support of the PDF is the well-known polarization ellipse that I'm sure you have seen in other contexts. But now we believe for the first time we derived now here this PDF for a randomly oriented transmitter with uniform distribution. And let me just say that you see here this bathtub curve here, rotated in terms of the ellipse. We get infinite probability density on the edge and a lower probability here in the center. We can see this as a preliminary step to now determine the distribution of H with random transmitter and random receiver. And if we can do this by marginalization of this result, and turns out that we cannot solve the integral in closed form, but we can do numerical integration. And we obtain a particularly interesting PDF. The support is now this rhombus here. And here you can see how this rhombus arises from the ellipses for different transmitter orientation. And we note that it's a two-dimensional manifold like the ellipse. And this is now the case in the near far-field transition here. Here R is similar to a wavelength. And when the link distance is much smaller or much larger than a wavelength, then this rhombus would degenerate to a one-dimensional. It would become a line. And the problem with that is that for a line, we are much more likely to have a realization close to zero. When we have this nice two-dimensional PDF support, then realization of H will usually be more likely to be far away from zero, and so we will have better fading behavior. This is polarization diversity. All right, and the performance implications are that the CDF is now not a square root for small values, but linear, so like in Rayleigh fading. And we get here this linear scaling for the outage capacity, and here this diversity exponent of 1 for the outage probability, which is the same as in Rayleigh fading. So Rayleigh fading, which is usually regarded as the worst case in radio propagation, is here actually would be an improvement for magnetic induction. And we can achieve this by purposefully operating the near far-field transition if the application allows for that. Here's the detailed result, which we are not going to discuss here. You can see it in the paper. And let me just summarize my talk now. What did we present? We presented a closed form description of the fading channel statistics between randomly oriented dipoles. And of course, with the main focus application is magnetic induction, which can often be modeled by dipoles. We presented various novel PDF results for the marginal distributions of alignment factors and for the ellipse and the rhombus. And we revealed the drastic outage behavior, especially in the near and far field regions. We remember the terrible scaling behavior, diversity exponent 1/2. And we see that if we have to operate in the near field region, then diversity concepts are very important. For example, 3-axis coils or a rotating source. And yeah, thank you very much for your attention. I hope it instigated some interest in the topic, and you are invited to have a look at the paper. Thank you very much.